Hello everyone, welcome to the SEG2020 VSP session. This video will present you a walkaway VSP survey for fractured basement imaging using random space shift reverse time migration. My name is Jingjing Zong, and my co-authors are Dr. Jizhong Yang, Dr. Arthur Chen, and Dr. Yunye Elita Li. On this video, we will start with an introduction to the survey area and the acquisition geometry. Next, the numerical wave field simulation will be shown to serve as an analog to understand the P and S wave field information. We will then talk about the VSP preprocessing, especially on the P and S wave separation part. Following that, we will see the P wave image by RSS-RTM and draw some conclusions on the current work. Finally, we will share with you 2 lines of ongoing work following the current results. Let's first revisit the vertical seismic profile with survey geometry. VSP surveys employ surface sources and borehole receivers and record high-quality multi-component wave fields. The receivers are often 3-component geophones that are clamped onto the wellbore while recording. Recently, the optic fibers become the cheaper alternative sensors and have a considerable potential for permanent monitoring. The sources can be either dynamite or vibroseismic track. The dynamite generates an impulsive source signature, while the vibroseismic track generates a sweep of vibration with varying frequencies. The VSP surveys are used to obtain rock properties and seismic images in the neighborhood of the wellbore. With the presence of subsurface reflectors, the main event a receiver would record include the downgoing direct arrivals, the downgoing multiples, the upgoing primary reflections, and the upgoing multiples. An example of the crowding shot gather on the receiver side is plotted with the horizontal axis at the increasing depth to the right, the vertical axis at the increasing time to the bottom. It displays a Z-component shot gather recorded by the geophone. On the other hand, the depth recording, which is a single direction along the borehole, shows the similar features, but somewhat different amplitude, noise level, frequency content, etc. The study area is located at a basin where highly productive reservoirs were found around and beneath the fractured basement. For example, those red areas indicate the discovered reservoirs. The fractured basement reservoirs pose great challenges to surface seismic exploration as they are associated with complex fault and fractured networks, strong heterogeneity, and distinguished seismic impedance contrast between the basement rocks and the surrounding sediments. In 2017, 2 walkaway VSPs were acquired at well location A and B to provide higher resolution image and to better delineate the highly faulted dipping structures. A surface seismic survey was carried out in the first place and illuminated the general structures and dipping features deeper in the section. The walkaway VSP surveys were acquired using a combination of dynamite and vibroseismic sources. The 3-component geophones record signals in the downhole locations with an interval of 20 meters. Well A penetrated less than 2 kilometers, while well B went deeper and penetrated through the basement top. In this talk, we present the survey carried at well B to show the dipping features of the basement top. There are a total of 267 shot locations with an interval of 25 meters on average. The geophones recorded 6 seconds data at a total of 126 levels from 500 to 3,000 meters measured depth. The surface offsets reaches 3 and 4 kilometers on either side of the well. We run numerical simulations to first understand the elastic wave fields. Based on the geologic model interpreted from the early surface seismic image, as well as the velocity and density surveys, a simplified model was built to feature the general structure. We run elastic wave field modeling using the SpecFilm packages published by the Princeton University, It is based on the spectrum element method. Examples of near offset shots are displayed next to the field shot gathers. While A is vertical well, the simulated main reflections are matching very well with the field records. The blue arrows mark the P-wave reflections, while the red arrows mark the converted shear wave reflections at the basement top. A main difference we notice between the simulated and the field record is the tube wave, which comes after the direct arrival with a slower velocity. The tube wave is not simulated, and it will be removed as a noise in the field record before imaging. The similarly good coherence between the simulated and field record repeats for well B in the displayed near offset shots. It indicates that we have a reasonable initial velocity model to start with. It's noticeable that the converted wave at the top of the basement is pretty strong, even at the near offset shots. Move on to the imaging strategy. As the acoustic RTM saves computational cost and employs a more straightforward imaging condition, it will be used in this study. However, it requires the separated P and S wave field. With the observations of strong shear wave conversions, we are reminded of the importance of proper wave field separation. Next, we will get into the data preparation with an emphasis on the wave field separation. Let's first look at the three component raw shot gathers that we're about to process. In this given near offset shot, downgoing P and S wave, upgoing P and S waves, and tube waves are seen. The task of preprocessing is to separate P and S waves in their downgoing and upgoing fields, and suppress noises such as the tube waves, multiples, etc. We follow a classic VSP processing flow to prepare the data, with a careful touch on the P and S wave field separation. The data was received after surface static correction. After the initial data preparation, including data loading, autocorrelation, stacking, we set up the source and receiver geometry. We sorted the data by the common shot gather and went through the trace editing to get rid of the anomalies. The P-wave first arrivals were picked at the Z component mostly and transferred to the other channels for later hologram analysis and wave field alignment. We redistributed the primary downgoing P and S wave energy using the two-step hologram rotations. After that, the medium filter were applied to separate downgoing and upgoing fields. The downgoing wave fields were then used to test the deconvolution parameters and will apply to the upgoing wave field. The downgoing wave field at near offset shot locations are often used to obtain the 1D velocity profile and Q factors. On the other hand, upgoing wave fields were further subject to the time-variant rotation to obtain the finally separated P and SV wave fields. Other enhancements such as FK filter and bandpass filters were then applied to remove some further noises. With a smooth velocity model, the separated P or S wave fields after deconvolution will be imaged using the RSS-RTM. Let's look at an example of the separated P and S wave field. Starting with the raw shot gathers, most energies are distributed in Z and X. Clear P and S reflections are seen at the top of the basement. After the first rotation, which is the horizontal rotation, between X and Y components, the downgoing P wave energy was maximized in Hmax channel and minimized in Hminimum channel. The second rotation, or sometimes referred as the vertical rotation, between Hmax and the Z channel further redistributed the maximized downgoing P wave energy into a direct channel, and the residuals onto a radial channel. In the displayed shot, most downgoing P wave and upgoing shear wave are distributed to direct channel after the vertical rotation. The radial channel contains more upgoing P wave energy. A 13-point median filter was then applied to separate the downgoing P waves. The reflections in this study largely remain in the outgoing field. Thus, we separated and enhanced P and shear wave reflections from the outgoing wave fields. The ray tracing-based time-variant rotation further redistributed the outgoing P wave into one channel and the residuals into another. The P and S wave reflections were gradually separated into two channels. Finally, we applied a FK filter to enhance the outgoing wave fields and deconvolution to improve the resolution as well as to suppress multiples. During acquisition, the walkaway line has some unavoidable minor deviations and discontinuities, while the borehole is slightly deviated at the bottom. Since the acquisition system still remains largely as a 2D system, we simplify the issue by projecting both shot and receiver arrays onto a 2D plane. We next implemented RSS-RTM to the field data. Let's quickly review the methodology and advantages of RSS-RTM over the conventional RTM. For conventional RTM, the migration image can be obtained by cross-correlating the forward-propagated wave field with the backward-propagated wave field. The seismic data can be reconstructed through this equation. When the migration velocity is inaccurate, the forward-propagated wave field cannot meet the backward-propagated wave field at the same location. Yang et al. Introduced an extra model dimension edge to the Green's function to accommodate the velocity error. According to the finite frequency wave propagation theory, the theoretical lateral resolution after migration is the half wavelength. So, the introduced special shift is a randomly assigned length within the lateral resolution limit at each step. The random assignment of the shift window allows a comparable computational cost as the conventional RTM. This way, the geological structures are expected to be enhanced constructively while the migration artifacts are supposed to be cancelled out destructively. In theory, the RSS-RTM can tolerate velocity flaws better than the conventional RTM while remain the same computational cost. Let's see a numerical test using the Marmosy model for the difference. The accurate velocity model is seen on the left, and we build a migration velocity model by smoothing the true velocity model with a 2D Gaussian function, whose vertical and horizontal correlation lengths are 400 meters. We built in a 10% bulk velocity model by applying a scaling factor of 90%. Showing up first is the RTM image, and then the RSS-RTM image. We notice a great improvement in the continuity of the geological structures in general. The noises and artifacts are effectively suppressed. In the circled areas, the RSS-RTM gives more focused image compared with the conventional RTM. The arrow indicates an example where artifacts are suppressed by the RSS-RTM. Given that, we're comfortable to apply the RSS-RTM to the field data where an accurate velocity model cannot be obtained. We used a smoothed velocity model used in the surface seismic for fair comparison. The VSP image was bordered in red and incorporated in the surface seismic image. It is obvious that the VSP image provides a higher resolution and a pronounced amount of details in its illumination range. To evaluate the value of the preprocessing effort, we also imaged the raw Z component. The image from the raw Z component is shown on the left. After wave field separations, a considerable amount of the noise has been reduced and more complete and coherent structures has been revealed by careful preprocessing, as we can see from the comparison. The downgoing wave field and the shear wave removal contribute to a lower noise level in general. The redistributed P-wave energy from all three components give rise to a more detailed and complete P image. On the other hand, although the conventional RTM has been increasingly used for VSP surveys and demonstrate the capability to deliver high-fidelity images while utilizing all seismic wave field types and not imposing limitations on velocity variations and reflector depth, it is very sensitive to velocity errors. A direct implementation of RTM to the field data may result in defocused migration image due to the uncertainties in the velocity model. RSS-RTM partially mitigate this problem by stacking the extended migration image along the subsurface offset axis within a half-wavelength constraint. The spatial shift at each time step is randomly assigned in order to reduce the computation cost. We implemented both conventional RTM and RSS-RTM. It is obvious that the RSS-RTM image appears to be more continuous and the migration smiles are effectively reduced. Combining the efforts of both careful wave field separations and the RSS-RTM, we hope to provide a better subsurface image for interpretation. To conclude, we have applied careful preprocessing and RSS-RTM to a walkaway VSP survey acquired around a fractured basement reservoir. It is verified that a proper wave field separation utilizing 3C information lays a foundation to improve the image quality. A more clear and complete P wave field after separation gives rise to a better P image with reduced noise level and enriched details. For field applications where the accurate velocity models are not necessarily available, RSS-RTM demonstrates the reliability of producing a good image. Set side by side with the surface seismic post-active migration, the VSP RSS-RTM image provides higher resolution and more details in its illumination range, which encourages better characterization of the fractured basement. Following the P-wave imaging success, we're working on two extended directions. First, on the comparison with the dust data. As the fiber optics record one-component data as opposed to the three-component geophone data, two questions are asked. 1. How does the dust data compare with the raw Z geophone data? And 2. What's the significance of the wave field separation in the dust data, and how do we handle it if a separation is needed? On the other hand, we're working on getting a shear wave image. As shown earlier, we have separated P and S reflections for imaging. The examples showed that the separated shear gathers are in good quality. The next challenge we have is to solve the shear wave velocity model building. Now this is the end of the video. We would like to acknowledge our sponsors and collaborators without whom this research couldn't be possible. The authors are sponsored by Petroleum Engineering Professorship Program of National University of Singapore. Dr. Jingjing Zong is also sponsored by State Key Laboratory of Marine Geology in Tongji University. We thank Dr. Gang Yu and BGP for sharing the field data and for the permission of publication. We would also like to thank Janusz Pajang for a lot of good discussions. Finally, yet importantly, thank you for watching. Please share your comments or suggestions by sending me an email.